Hi everyone, in this video we are covering the derivative chain rule for our Calculus for Business course. And in order to really get the derivative chain rule, I want to remind you about something from algebra class called function composition. And the idea of composing two functions is that you're going to kind of put one function inside of the other function. And this brings to mind, a YouTube video I watched years ago where this guy was preparing for like Thanksgiving, right? And he had a turkey, and inside of his turkey, he also put a chicken like inside the turkey. So he had this little chicken thing, and he actually put it inside the turkey before cooking the turkey in the turkey roaster. And so for some reason, this image always comes to mind whenever we do function composition, because function composition is all about recognizing which function is going to be the turkey function, which function will be the chicken function, and how do you correctly place the chicken function inside the turkey function. So to give you an example of what I'm talking about, and again, I'm really hoping this is just a refresher from your last algebra course, but the idea here, if we check this one out, I have my f function, which is typically denoted f of x, but right here I have f of g of x. So notice what I have is I squished a g of x function inside of the f of x function. So where the input normally goes, I actually wrote g of x. And if I do that, and I use these definitions for f of x and for g of x, then that means putting the g of x where the x goes would give me the function f of g of x to be pi times, well, it's not x anymore, it's g of x. And g of x, the definition of g of x here is just the natural log function. So this is natural log of x squared. And so this is the whole idea, is that you're just going to replace x everywhere with whatever you put as the input to the function and see what happens. And so I will change pen colors to take a look at this one. The g of x function, as defined, is just the natural log function. So if I ask about g of f of x, well then instead of x, I'm going to write natural log of f of x. And if I then say, well, f of x, what is that? That's just pi x squared. Then my g of f of x function is the natural log of pi x squared. And a couple more. If I compose f with itself, so I let f both be the turkey and the chicken, then we write f of x as pi x squared. F of x would then be pi, and then instead of x squared, I'm going to write f of x squared, right? So whatever I put in my input of my function replaces the x. This means that f of x is going to be pi times pi x squared all squared. And you could even simplify this further and say, well, this is pi cube x to the fourth, right? If I square pi, it's pi times x squared times pi times x squared. And there's one more example. If I compose the function g with itself, I'll put this in blue. So g of x is just that natural log function, and so g of x would be natural log of g of x, and so g of x is then natural log of x. Okay, no way to simplify that though. But hopefully you're getting the idea, and you know what I mean then later whenever I say inside function, outside function, and so on. And sometimes in calculus, we're going to recognize that a function is just a composition of two simpler functions. All right, so maybe I have this function capital C, and I notice, oh, that capital C function, that's just f composed with g. And if we want to find the derivative of a composition of functions, then there's going to be a shortcut to help us with that. And we call that shortcut the derivative chain rule. And so what this says is taking the derivative of that capital C function it's going to require us to take the derivative of the outside function, still using the inside function as the input, and then we're going to multiply by that derivative of the inside function, just at the end there. And I'm going to point this out too. Using different notation, you might see it written like that. In fact, I think the textbook we're using this semester also has it written both ways. So if you have y as a function of x, then what you're going to do is you're going to find out what function u of x is really helpful as kind of an intermediate function. All right, so let's take a look at this. I have a function c, capital C. It's a function of x. And what I want to do is I want to find c prime of x. And so using that rule above, this is going to be like f prime of g of x times g prime of x. Okay, so far so good. Using that rule right there. But what we don't know yet is what is f of x and what is g of x. Well, actually, this composition rule, or this derivative chain rule, only works if I define my c function as a composition of two functions, where I'm going to use f to denote my outside function and g to denote the inside function. And looking at this really closely, I really invite you to pause the video and ask yourself, what would be the outside function, what would be the inside function? Pause the video right now and take a moment to think about that, and we will share the answer here in 3 seconds. So what I see when I look at this c of x function, I say that outside function must be the function x to the 5th. And my inside function, that must be the function 3x plus 2. And the reason I say that is because then whenever I say that my whole function is f composed with g, well then my f function is just x to the 5th, but instead this is going to be g of x to the 5th power, and g of x is just 3x plus 2, so I get 3x plus 2 to the 5th power. So this works to get my c function whenever I actually compose these two. And so I've actually picked a good function here for my outside function, which I'm calling f of x, and also my inside function, which I'm calling g of x. So I made the right choices. And now that I've made the right choices, I can actually, take this derivative formula over here, right? C prime of x is equal to f prime. Ooh, well, I actually need to calculate f prime, don't I? So this is my f function. Using the derivative power rule, tells me that f prime will be 5x to the 4th. So I write f prime of g of x. Oops, that's another thing I need to figure out, huh? So then writing f prime not just of x, but f prime of g of x would be 5 times g of x to the 4th power, which is going to be 5 times 3x plus 2 to the 4th power. So then this bit becomes 5 times 3x plus 2 to the 4th power. And then this times g prime of x function, well, finding g prime of x is just going to be 3 according to my derivative power rule. So I multiply by 3 at the end, and that is my solution for this particular derivative. Not too bad. Not too bad. And if that was confusing to you, I feel like we have a few more examples coming up, and so hopefully you get the hang of it. Seeing several examples of a particular derivative rule is always nice. So I've got this, and it's asking me to find what is the derivative of y with respect to x. That's what the dy over dx means. And I have a particular rule for this. That is to say that the derivative of y with respect to x is equal to the derivative of y with respect to some function u of x times the derivative of u of x divided by derivative of x. And personally, I think that this version, this notation to represent the chain rule, is neat to me. I like this notation a lot because you can kind of see whenever I have that du, it's representing a small change in this value slash function. It's representing a small change in u. And if I have the small change in u in the numerator and the small change in u in the denominator, you can see how those would cancel out then. And you'd be left with dy over dx. And so for me, it's really easy to remember this version of the chain rule. And while I say that, it's also important to see how this is equivalent to the chain rule written with our other derivative notation. You can see how it's actually the same. Now, we just have to find what would be a convenient function to let u be. What is a convenient function u of x? So that would actually help us to take this derivative. Well, there's something I see that appears twice in this particular function. I see 4x minus 1, and it actually appears twice here. And so I'm just going to let u of x be the function 4x minus 1. Okay? So now, instead of writing y as a function of x, I might write y is equal to 2u squared plus 3u. And if I write the derivative of y with respect to u, this would be, well, 4u plus 3. Nice. All good. In fact, let me now find, for this u function, what's the derivative of u with respect to x. And this would be 4. And so going back over here, my formula from the chain rule tells me dy dx is equal to, well, dy du is 4u plus 3 times du dx is 4. And the last step here is to make this again in terms of x. And so to make this in terms of x, this is actually pretty easy. Where it says u, I'm just going to replace that with the formula for u. So that's 4x minus 1. So 4 times 4x minus 1 plus 3 all times 4, that is the formula for the derivative of y with respect to x. Nice. So one more example. And this is telling me find f prime of t, so find the derivative of this function. And this is a typo. That should be 4t plus 7. So let me just scratch this out for a moment and write that this is 6 square root 4t plus 7. Much better. And, again, let's look. Did I write that right? Yeah, I guess I did. There we go. Let's write this in a way that makes this look a little bit nicer. Let's come up with a kind of intermediate function here where we're going to call it u again. So we're going to let u equal 4t plus 7 because that's underneath the square root. And I know how to take the derivative of like square root t. And if you don't remember, go back to my video about the power rule for how to take the derivative of square root t. But I don't know how to take the derivative of square root 4t plus 7. So let me just simplify 4t plus 7 into one variable, which I'll call u. This becomes 6 times square root u. And this, again, is u to the 1/2 power. And my derivative power rule tells me that this is going to be 6 times 1/2 times u to the negative 1/2 power. So very good here. And, what I've done is I've actually said this is my f function Oops, that's not right. Sorry. Ignore that. I have to erase it. That was bad. What I've done so right now, going from here to here, is instead of writing my f function, now I've taken the derivative of f with respect to u. All right. And so thinking about the chain rule, tells me that if I'm trying to take the derivative of f with respect to x, and by the way, oh man, I keep saying x. It's a hard habit to break. I want to take the derivative of f with respect to t. Because after all, this right here, f prime of t, that just is telling me the derivative of f with respect to t. Remember, there's more than one way to talk about the derivative, or there's more than one way to write the derivative. So what I'm trying to find is f prime of t, and this is just the same thing in different notation as saying df dt. And according to my chain rule, this would be the same thing as df du times du dt, and you can see how the little du's are going to cancel out. And I've already found df du. That's pretty good. Now let's find du dt. So the derivative of u with respect to t, again, derivative power rule tells me that's the number 4. And so using this derivative chain rule, well, df du is going to be 6 times 1/2 times u to the negative half power. And I also multiply by du dt, which is 4. So simplifying, 6 times 1/2 is 3, 3 times 4 is 12, so this is 12u to the negative half power. And remember, u is just 4t plus 7, so I write 12 times 4t plus 7 to the negative half power. And you remember what the negative half power means, right? So we have 12 over square root 4t plus 7. So the negative exponent puts it in the denominator, and then the half means square root. An exponent of half means square root, so there we go. One more example for this video, and this is kind of an application, it's a word problem. And this says the demand for a certain fidget toy is a function of the price, and I'm going to write that function n as being n equals 3500 times square root 8 minus 1/2 p squared. So n is demand and p is price. So let's find the demand when price is $3, and so actually that's not even a derivative. I just have to take 3500 times square root of 8 minus 1/2 times 3 squared. So that means 3 squared is 9, and so we're talking about half of 9, so this is going to be 8 minus 4.5, which is 3500 times square root of, what, 3.5? And I have no idea what square root of 3.5 is. It's going to be a little bit less than 2, right? Let me get out a calculator. So here we go. Square root of 3.5, 1.87. And so 3,500 times something a little bit less than 2 is a little bit less than 7,000. So times 3,500 is going to be 6,548. Okay. So that's the demand. All it is plugging in your price for P to get your demand. And what we're asked next is find the rate of change of demand with respect to price. And so remember, derivatives describe rates of change. And so this is asking find the derivative of demand with respect to price. So the derivative of demand with respect to price looks like that. And this is asking for then the derivative of this function right here, right? And you're going to see that this requires the chain rule. And what I'm going to use is just some intermediate function, which I'll name u for consistency. But using a u function is going to make this easier to take that derivative. And remember, this is nothing but the formula for the chain rule, where I've actually plugged in the names of my function and my variables. So the big question, maybe the most difficult thing in chain rule, is what should u be? And in this case, I see a big square root, and I know how to take the derivative of square root of a variable, but I don't know how to take the square root of 8 minus half p squared. And so maybe I'll just let u be 8 minus half p squared, and that will simplify my n function to where n is just going to be 3500 times square root of u. So now if I want to take the derivative of n with respect to u, this will just be 3500 times 1/2 times u to the negative half power. And I also, it looks like I need to take the derivative of u with respect to p. And so looking at this u formula, the derivative of u with respect to p, well, that 2 comes down and it looks like it's just going to be negative p. All right. So then the derivative here of n with respect to p is going to be dn du, which is 3500 times 1/2 times u to the negative half power, times du dp, which is just negative p. So simplifying this, and also replacing u with the definition of u, is going to be 3500 divided by 2 times a negative times p. And then what's the definition of u to the negative half power? Well, that would be 1 over square root of 8 minus 1/2 p squared.